So now let's get back to our Gauss-Markov theorem. We had seen already that we are trying to make it more general. We said that we are going to remove that condition of that x transpose x being non-singular. We do not want that. We want to work with any general x. And you have also guessed that we cannot anymore work with just any c. We need to put some further restriction on c. Now, that immediately implies that what kind of restriction should we put on C, and we discussed that, and we found that one restriction that is kind of the very basic minimal restriction that we should put is that we must have C belonging to row space of X, because if that is not the case, it is not even a meaningful problem to try to estimate C beta. Nobody can meaningfully estimate C beta, let alone obtain blue or whatever. So that is the basic minimal condition. Interestingly, that is all that we need. So that minimal condition is enough for us. We can then say precisely the same theorem, C prime beta hat will be the unique blue of C prime beta. So that is the general form of Gauss-Markov theorem. Now, how to prove this? The proof is pretty straightforward and follows essentially the same argument what we used for proving that special case, with one catch, and that is a serious catch. You might expect, suppose I try to show that it is unbiased, just do that. Well, how will you do that? You apply expectation on that, and you expect C being a constant thing, expectation will go through it, so C will come out of expectation and it will work with expectation of beta hat, right? No, that won't work. Simply because once I have dropped the condition that x prime x is non-singular, beta hat ceases to be uniquely defined. There are infinitely many possible beta hats, all of them least square estimator. Which one of them are you talking about? So you cannot say, I will take expectation of that. That's where we have to use a little linear algebraic trick, but after that everything will follow through and exactly the same proof as in the simple case. Once we have settled this issue, what is exactly meant by C beta hat when beta hat is not even uniquely defined? For that, let us focus our attention on this condition C belonging to row space of X. You understand that row space of X is same as column space of X transpose X. No problem with that, because row space of X is column space of X, which contains anyway column space of X transpose X. Their dimensions being same, they are actually the same. So C actually belongs to column space of X transpose X. What does that mean? If something belongs to column space of X transpose X, you can immediately say that C may be expressed as that matrix X transpose X times some vector. No problem with that, because the columns of X, you take a linear combination of the columns of X and all the coefficients you put here in D. So C is X transpose X into T. So now let us see what happens when I work with C transpose beta hat. So that is the quantity, the C transpose beta hat. That is the fellow which we have to work with. We know beta hat is not unique. You take any beta hat, any least square estimator beta hat, C transpose this, then this becomes C transpose is D transpose X transpose X. Remember, this is a symmetric matrix. So taking transpose has no effect on that, times beta hat. Now notice that beta hat, whatever it is a solution of the normal equations. What was the normal equation? X transpose X beta hat equals X transpose Y. So whatever beta hat you take, X transpose X beta hat must be equal to X transpose Y. So you see, it is here that the non-uniqueness of beta hat nicely goes away. So now you obtain something which is completely free of beta hat. No non-uniqueness plagues this expression. It is just D prime X transpose Y. Find quantity. This is a fixed known vector. X is a known matrix fixed. Remember, D is completely known because C you are given, that is what you are trying to estimate, C prime beta, X you are given. So you can express this and obtain that. D may not be unique, but you just take any one such D, that is enough. It will always give you the same C. And now, so it is a completely known fixed vector and y is the random thing. So you can find expectation etc. using this expression. So instead of when you apply expectation taking c out and applying the expectation on beta hat, you take this d prime x prime out and apply the expectation on y. So once you do this little trick, now the rest of the proof of the Gauss-Markov theorem remains just unaltered. So I will leave that as an exercise, and anyway if you have problem you can always look up our textbook. Now in our textbook there is a little kind of weird thing. The textbook assumes that we are working with x prime x non-singular, yet the textbook uses this proof. So if you are really assuming that x transpose x is a non-singular matrix, then you really do not need to go through all these things. You do not even need to define what is meant by estimable, because then everything will be estimable. That's why in the simple version I could work with any c. So the book actually works with x prime x being non-singular but provides this general proof. So that is kind of weird, but this is the general form.